Good afternoon and good morning, everyone. I see in the people list some names that I don't know, and then probably you don't know me as well. I used to work, I still work for GN 1 day a week. I used to work full-time for a very long time at GN. And now I mostly work at the university here in Eindhoven. And I'd like to give a presentation on the work that we do at the university, and we, of course, on the work that we do for GN. So let me share my slides. First slide. This is an aerial view of the campus of the Technical University in Eindhoven. And the first building, once you walk from the train station, is this building. And this is the building where GN sits. And if you would continue walking to the, it's about 200, 300 meters to the building at the end. At the other end of campus, this is the electrical engineering building. And this is where I sit with my research group, which is called Bias Lab. And so I walk back and forth a few times a week. And this is a view in the summer, by the way. This is not how it looks like today. So what I'm going to talk about first about our motivation and ambition. Well, I need to explain what I mean by natural situated hearing aid algorithm design, and I'll talk about that. Then I'll talk about what I think is some breakthrough science, namely the physics of neural computation. And I'm going to call that, after some explanation, variational free energy minimization, or abbreviated VFEM. And that's going to be crucial in everything we do. So it's going to be important how to realize that variational free energy minimization. And we built a toolbox for that. That toolbox is called RxInfer. I'm going to talk a bit about RxInfer. And then, of course, how to use this variational free energy minimization for the task that we are trying to implement, natural situated hearing aid algorithm design. And then in the end, what does it mean if this is all going to work, and is it going to work? And that's then I'll be ready for questions. So first, some motivation. And I've shown this slide a few times before. So here's a patient that gets her hearing aid and she's happy. She has left the audiologist, and then, you know, always something happens in a restaurant. She can't hear her conversation partner, and she goes back to the audiologist. And if the audiologist cannot fix it, it goes to the tables of the engineers, and then they work on it for a while, and then we get product people and marketing and sales people, and there is a design iteration, and that may take, as you know, even up to 2 years. So that is, and there's a lot of expert people in the loop here, right? I mean, at least a few hundred, if you count everybody from engineers to salespeople and marketing and audiologists. So that brings about a slow and expensive design cycle, and in the end, that's not satisfactory for the patient often, because, you know, if it takes 2 years for a problem to get solved, then the hearing aid may end up in the drawer. So that's not optimal, in particular if you compare this how the brain designs in the world, because the brain is also an algorithm designer for, I mean, you can learn how to ride a bike, or how to speak Japanese, or how to recognize objects, and also you can learn how to hear and recognize languages and so forth. And this kind of design is all in real time. There's no engineers in the loop, and so lots of advantages, it seems. I would like to bring this kind of design, the way the brain designs in the field, to our design loop. So this is now going to be in a real-time design loop. When she has a problem, she will appraise like that, and there will be an agent on her smartwatch or phone that will immediately update the algorithm. And this can go on a few times, but the crucial thing is it's a real-time design loop, just like the brain does. And yeah, since you cannot bring your audiologist or your hearing aid engineer everywhere you go in life, we have to replace, for in situ design, for situated design, we have to replace, let's say, the designer by an automated designer. So, and we call that an agent. So that's our goal. And why do we want to do that? Well, I mentioned a few things, but if you think about it deeper, there are lots of areas where brains or natural design is actually completely outpaces engineered design, right? So, for instance, as I mentioned, design of algorithms by brains is completely spontaneous and automated. It's whereas we need lots of human experts. We have offline long design cycles. This all seems to just happen in real time. You just go out and ride your bike, you fall, you correct, and after a while you know how to ride a bike. You don't need to learn from a big database like all the AI programs seem to do. Crucially, and this is a very interesting thing, you will do everything with the same brain, whether you want to learn Japanese or learn how to ride a bike. You do it with the same brain, and interestingly, there is just one solution approach to basically every problem in the brain. It's of course very robust. You lose 10,000 neurons every day, and it doesn't break down, and power consumption is, you know, the comparison is not even funny, right? For the same computational power, the brain is at least 1 million times cheaper in terms of power consumption. So all of these are fantastic properties that we would love to have when we design our algorithms, but we will not get it unless we study how the brain does it, right? And so that's what we set out to do. We want to learn how does the brain actually compute. So I'm going back now to something really basic physics, right? Here's a ball. Let's say I just kick that ball at t0, and that ball takes this path here, and at t1 is going to be at this point, right? And here's a mass. So the question is, why does the ball take this path? This black path? Why doesn't it take this red path or some other alternative path? How does the ball even know what to do? And if you're a physicist, you will say, well, you know, the ball just follows physical law. So Newton's second law, force equals mass times acceleration. And that's completely correct. Right, and the force it's a gravitational field, which technically means that the force is the gradient of a potential field. You have a gravitational potential field, and if you take the gradient with respect to the height x, then you get the force. And yeah, this is correct. Newton's law. If you use Newton's law, you can derive that you take the black path. There is, however, another thing in physics that is more fundamental than Newton's law, and that is the principle of least action. And the principle of least action says I can compute for any path, also for this red path and for the black path, something called an action, which is a variable. It's and among all the or the path that is taken will be the path of least action. So the action for the red path will be greater than the action for the actually taken path. And what does that mean in practice? Well, it means this. In nature, energy differences of any kind are neutralized as fast as possible. So if we do that now for this ball, well, what kind of energies does this ball have? It moves, so it has kinetic energy, and it's in a gravitational field, so it has potential energy. So let's take that difference. Let's define a function L, which technically is a Lagrangian, and that's why it's called L. But it's a difference between the kinetic energy n times the derivative of the height squared divided by 2 is kinetic energy minus the potential energy. By the way, I'm I'm doing some math here, not for you to follow in detail all the math. I just do this as sort of an illustration that this is real. This is not some hypothesis. So you can forget about this math, but I want you to kind of follow the argument. So the idea of the principle of least action is that in nature, energy differences, and there is an energy difference between kinetic and potential energy for this ball, this is minimized as fast as possible. That's how the world works. So let's take the integral of this over time. So take an integral of this energy difference over time, and that's in physics called the action. This is for the chosen path, or for the actual path is minimal. So I need to take a derivative now, but this is a derivative of an integral of a function, and so that leads to, it's not a simple derivative, it's called a variational derivative, and or functional derivative. It leads to a set of equations, Euler-Lagrange equations. If I now substitute this Lagrangian in here, which I do here, then I get out this. This is the result. This is the result of applying the principle of least action. Hey, that's actually Newton's law. I just derived Newton's law. Newton's law is not the most fundamental thing. Newton's law is just the principle of least action for big moving things in this world. We can derive Newton's law from the principle of least action. Principle of least action is more fundamental. So we can derive a theory for movement of big things by choosing as a Lagrangian as the difference of kinetic and potential energy, and that leads to all of Newton's laws. We can also apply the principle of least action to movement of many little things. You choose a different Lagrangians and you can derive all of statistical mechanics and thermodynamics. You can apply the principle of least action to movement of small things. You choose a different Lagrangian. You have to, of course, use the proper Lagrangian, and you can derive the laws of quantum mechanics. We can continue to do that for other fields, electrodynamics, particle dynamics, and so forth. Physicists like to write the Lagrangian for all of physics on a mug. And this is what they call the Lagrangian of the standard model. This is the Lagrangian for all of physics. If you minimize this over time, you derive everything of physics. So this is more fundamental than a law like Maxwell's laws or Newton's laws. This is a principle. You can derive laws from this. Now, the interesting thing is that, yeah, brains or we can assume that they submit to the laws of physics, right? So isn't there a principle of least action for information processing in the brain? Why not? I mean, brains are physical systems. So is there a theory for movement of beliefs, thoughts, learning, perception, behavior, attention in brains? And there is. Right? This is Carl Friston, and Carl Friston says, yes, there is a physics for movement of beliefs. Following from the principle of least action, the brain must follow the principle of least action because it's a physical system. Brains minimize something called variational free energy in least time. The Lagrangian for the brain is this. It's expressed here as a complexity minus accuracy, which are two terms people use in machine learning, but it's also kinetic energy minus potential energy, if you will. The crucial thing is this is all that brains do. Just like a ball, all it does is it moves and it minimizes the difference between two energy forms. This is also what brains do. And by doing so, brains change beliefs expressed in probability distributions. You see here a P of S and a Q of S. Those are probability distributions. Those express beliefs, your thoughts, things that you learn, your perception, your cognition, your actions, your behavior. attention mechanisms. Everything follows or emerges from minimizing this this Lagrangian. Why is that interesting? Well, it's interesting by itself, but there's this Lagrangian, this variation of free energy, has another property. Okay, one more thing. Why should we listen even to Carl Friston? Well, he is the most influential brain scientist of the modern era. You can he's ranked #1 by a computer program that tries to rank him, but you can also look that up on the internet. His H index is like 260 or something. He's a very, very impressive guy. So we should listen to him. Why is it interesting that brains minimize variational free energy? Well, variational free energy minimization in least time leads to Bayesian inference. What is Bayesian inference? Bayesian inference means that we do information processing by manipulating probabilities by probability theory. We commit to probability theory. Why is that good? Well, because it's provably optimal for information processing. This is explained in the book Probability Theory of Edwin James, 2003, but it goes back all the way to around 1940s by...
Ich habe schon einen coolen Job.
Sorry?
Ich kann auf dem Bett liegen und...
Oh, sorry.
Is there a question in English for me?
No, sorry.
Okay, no problem. If I go too fast, or you can also just jump in and ask me to slow down, right? The point I want to make is that so brains minimize this thing. Don't worry about what it looks like. It's just a function. By minimizing this, brains, if a brain would minimize this function globally, that means perfectly, we would do provably optimal information processing, right? Think of Mr. Spock in Star Trek. However, we cannot minimize this globally. Our brains are not perfect, so we do approximately optimal information processing, right? We make mistakes, but at least our brains try to do the right thing. And I think that's quite amazing, right? The conclusion is brains follow the laws of physics. Of course, what else? That means they must follow the principle of least action. Well, the specific conditions under which brains operate, namely they are separated from their environment but have an open communications through sensory channels, your eyes, your ears, and also they have effector channels, right, through your muscles. In that kind of configuration, brains do automated optimal information processing. And that means that with this kind of information processing, if you feed it a lot of, let's say, acoustic data, and there's speech in there, and it happens to be important to learn more, then brains can learn to understand speech. And it does so by just minimizing this functional. Hearing is subject to minimizing dysfunctional. It must be, because it's the only thing that brains do in terms of information processing. And so the interesting thing then for me is, can we use this variational free energy minimization and nothing else? So just variational free energy minimization to program artificially intelligent behavior on silicon, right? Because we have to implement our stuff on a chip and not in a brain itself. So this is the question that we ask ourselves in our lab. Can we sort of emulate or simulate what brains do on a regular computer? And with that, if I can do that, then yeah, maybe I can also learn hearing under situated conditions, just like brains do. So then I'm going to talk about if we can do that. Can we minimize variational free energy? Can we simulate that? Well, there is a problem that the computational task is enormous, because what we really are asked to do, what a brain does, is it automates in a spontaneous way variational free energy, minimizes variational free energy over 10 to the power 14 synapses. So that's 1,000 trillion synapses in a highly time varying function, right? It's the variational free energy happens to be a function of your sensory inputs. So for vision, there is like 6 megabytes per second is hitting your retina. And it has to be minimized in real time. If the brain doesn't minimize this in real time, you cannot drive a car, right? You will just hit the other car. And the brain consumes less than 20 watts, right? The cortex only consumes like 4 watts, which is a bicycle light consumption. So we have an extremely tough and large computational task, extremely high dimensional time varying function that they need to minimize with extremely low computational resource. It has to be done in real time for just a few watts. In engineering terms, what the brain does is unheard of, completely impossible. I mean, if you worked a bit with optimization, you know that even if you go beyond 5, 6, 7 variables, you're already in trouble. And the brain has 10 to the power 14, let's say, variables. So this is a huge problem, right? This is not something, and this is also why so far nobody has really built a brain, right? So this is, if we want to try this way, it's going to be a multi-year, multi-person effort. And it's not like something you give a master student, right? And I think it's the greatest challenge of the next decade for the next generation of AI students. If they're interested in building AI systems that, let's say, try to learn and pay attention in ways that brains do. So in my group, we try to build a toolbox for this. We try to build a toolbox for real-time variational free energy minimization, or as it's sometimes called, Bayesian mechanics, right? We have classical mechanics, the mechanics of big things, and we have particle mechanics, and Bayesian mechanics is the mechanics of information processing as derived by minimizing or by following from the principle of least action. So we have this this toolbox. This is, if you would go to rxinfer.ml, what it says here at the bottom, you will see a website for this toolbox. We build a toolbox that tries to implement real-time variational free energy minimization. It will do so as the animation kind of shows. It will build a network, and in that network, messages are passed from nodes to nodes, and as a result, you kind of see probability distributions are changing. You can think of that, your beliefs, your thoughts are changing while messages are being passed between nodes. So this very much looks like, let's say a brain network, right? Which is also a graph of neurons that pass messages, and as a result of that, your thoughts change. Is that by accident? No. I'm going to go to the next slide. I'm gonna skip. What I want to say here is that graphs implement something called the distributive law. If I want to compute A times C plus A times D plus B times C plus B times D, that is the same, as you know, as A plus B times C plus D, right? If I just, let's say, write what's at the bottom here, if I multiply everything out, I will get what's on the top here. Now, what's on the top here, in order to compute it as it's written down, I need 1, 2, 3, 4 multiplications and 3 summations. If I want to compute this at the bottom, which comes out to be the same, I only have 1 multiplication and 2 summations. So at the expression at the bottom is computationally much simpler than the expression on top, but it computes the same thing. It turns out that the operations that the brain needs to do for variational free energy minimization are of this kind. It needs to compute, let's say, what's on the top here. And if I want to do that in an efficient way, I need to use the distributive law. And that translates in, then you must do it in a network and you must pass messages just like a brain does. That's basically how you implement this cheaply. It kind of follows. There is no choice. We have to use a network and pass messages on that network. That's how brains do it, not because it's just cool, but just because it's the only way to do this cheaply. So it's no accident that the brain is a network, and it's no accident that our toolbox is also based on a graph that passes messages. Now and then, yeah, we spent a whole lot of time on building this toolbox and making it better, with the hope that once that works, we can put it in a box. Let's say let it run on a Raspberry Pi, or perhaps in a watch, and we can get this communication going on in real time in the field. And all that's going on in this system here, it would be, yeah, variational free energy minimization, just like the collection of 300 experts in the field at Resound. They also collectively implement free energy. Their collective brains do just one thing, minimizing variational free energy. And RxInfer would do hopefully the same thing. And in this way, we hope to automate basically, yeah, all these great properties that, of natural design, and get rid or kind of hopefully improve the not so great properties of the current engineering design cycle, right? So hopefully we go to automated design and very robust and low power consumption, those kinds of things. And then in the very long term, of course, you want to implement RxInfer even in the hearing aid, and then I don't need a watch anymore or any other device. And yeah, then we have really going on, let's say, in a hearing aid, the same type of computations as we would have in our brain, right? So that's the plan. Now, how far are we? First we need to know what kind of model really. Variational free energy minimization is something you do on a model, and to know what kind of model a brain works is easiest to show that in the context of vision, right? If you look at this, it's basically a vegetable bowl, and I turn it upside down, the first thing you will probably see is a gardener, right? A face. And the first thing you think of is not an upside down vegetable bowl. Just like on the left-hand side, the first thing you think of is a vegetable bowl and not an upside down face. And but of course, this picture here on the right has the same pixels as on the left. So there is just as much information about the vegetable bowl on the picture on the right than on the picture on the left. And still here you see a face, and here you see a vegetable bowl. And the reason is that perception is not just determined by what you see, but it's a fusion of what you predict you will see. There is a model in the brain that predicts sensory inputs, and that gets matched by actual inputs, and sort of the fusion or best match is what you see. Now, since we see in the real world many more straight up faces than upside down vegetable bowls, we have a much higher probability for seeing straight up faces than upside down vegetable bowls, and that's why you see here a straight up face. And we also see in the real world many more straight up vegetable bowls than upside down faces, and that's why you see here a straight up vegetable bowl. So this is known very long time about the brain. The brain is a generative model for its sensory observations. It means it tries to generate first or predict first your sensorium, your sensory impression, and then all the incoming data does is sort of correct that that prediction. There's also a whole bunch of theory around this, starting with literature in the 1970s about, well, if you want to control your environment, which is what we do, you must be a model of that system. And so Conant and Ashby, which are sort of they sort of started this field of cybernetics, or they were very big guys in cybernetics in the 1970s, already said that the theorem, this good regulator theorem, has the interesting corollary that the living brain, so far as it is to be successful and efficient as a regulator for survival, must proceed in learning by the formulation of a model of its environment, meaning the brain primarily works inside out. It's most of the messages, more than 80% of, let's say, our information stream is prediction towards our eyes and our ears, and only 20%, let's say, is bottom up, going from the sensory organs to the, let's say, to the cortex. So perception, cognition, everything is based on inference in a generative model for its sensorium, and we all know about the recent successes of generative models like GPT and Bert and all that stuff. So they just started now with generative modeling, and it's a big success. What they're not doing is Bayesian generative modeling, and so I think that will be the big next wave, maybe in 5 to 10 years, when they start being Bayesian about it. The Bayesian is absolutely needed if you go to, let's say, the situated design. GPT is brilliant, but you cannot tell ChatGPT to go out and learn how to ride a bike, right? It's knowledge based. It's not reasoning based. It's brilliant at compressing an enormous amount of data in a couple of billion parameters and using that to make predictions. But it's not very good in a dynamic environment, learning as fast as possible what the world is like and how to manipulate that world. That's not what ChatGPT is good at. In order to do that, I call that situated learning. We need to go to Bayesian generative modeling like brains do. So unfortunately, this circuit is what we have in our hearing aid is not a generative circuit. So it's beautiful, it works well, but it cannot extend it to proper, let's say, situated design. So what proper situated design would look like is, so here's the hearing aid, and what would you have in the hearing aid? Well, it tries to generate your sensory inputs. Here's our sensor, right? So what comes in? Some sounds from an airplane, somebody speaking, some bird sounds. So inside, I have a generative model that models sounds like from a bird, and the arrow, the generative direction is from the bird to the microphone, and from the speaker to the microphone, and from the plane to the microphone, and maybe even other sources. And then that creates a prediction for sensory inputs. And then when I actually hear the sensory inputs, it tries to correct that and then it passes, let's say, corrections back to, and tries to, in that way, decompose this incoming mixture into the individual sources. That process of decomposing the mixture of inputs into the individual sources happens by, well, variational free energy minimization, because that's the only thing that the brain does. We call that inference, or Bayesian inference, or variational free energy minimization. And that's the processing in the direction from the microphone to the sources. Once we have decomposed the incoming signal into the sources, and that's also kind of what the brain does, yeah, then it's a matter of which one do you want to hear and how loud, right? So then the real hearing aid assistant is very simple, is very trivial once you have the sources, right? It's just like, oh, I want to hear this one and a little bit of these two and combine them to the microphone or to the speaker, and there you go. And if he's not happy, then he will just say, well, change it a little bit, but it's going to be easy because there's just 2 or 3 parameters I need to turn, right? There's not 100 parameters in this hearing aid. This part in red is completely self-supervised, self-organizing. There's no input from the user. This is where the heavy stuff, let's say the variation of free energy minimization is ongoing. How you want to present that to a user, that's personalizable, but that's also trivial. It's a very simple agent. So this is the hearing aid that we are going to try to build, and the difficult part will be to do this, the inference, basically the blind source separation. So this is what it looks like now. Here's a graph inside, and we've built this graph, and I can kind of explain it by saying, yeah, here is it says AR. It's actually a hierarchical autoregressive model, which is a dynamic model for bird sounds. And here's another one for speech sounds. And here they get added up, and they get and predict here now my my inputs. And then once the input comes in, there's variation of free energy minimization going on, which kind of corrects these predictions. And then I take these two and I multiply them with gains, and I sum them and go to the hearing output. So you kind of recognize in this circuit what I did. And then here is C. This is context evolution, because we want our gains to be dependent on where I walk around, what kind of context. So there's context sensing, and so that's kind of how this works. I'm not sure when I joined if I actually, let's see, I can't.
I think for sharing the presentation, you then should include computer sound, right?
Yeah, I don't know if I did that. So I'm gonna play. Do you hear anything?
No.
Okay, sorry then. I will. I make this presentation, of course, available, and so there is about a 4 dB improvement in our system. So from input to output, we don't get always 4 dB. Depends on which sounds, and sometimes it's a bit more, sometimes a bit less. But on average, the current implementation, it's pretty much completely self-organized. So we don't have big databases. We just run it on incoming speech and other sounds, and then it gets about 4 dB. It's not real time yet. Our tool, we're working on a toolbox, but that's about where we are. But yeah, I would have to go out and go in out of Teams, so I think that takes too long, and I apologize for not checking the flag. I'm going to the next slide. Almost done, right? So what if this would work? Right? What if, I mean, so this is where we are. We get about 4 dB. I cannot guarantee it for every sound, but let's say that in a few years it's all robust and it works, and we have a nice hearing aid. This is what's in it for resound, and yeah, I wrote it down, and I'm going to read it. That's not the best way probably, but I'm going to tell this story here. So here's a problem that I think for a company. So assume you have a company, hear you, right? And it develops a product with some state-of-the-art audio processing capability. Let's say to support an over-the-counter hearing product. Well, you need to build this. You need to develop it. You need 100 professionals to develop this product. 25 for research, 25 for software, 25 for hardware, 25 for testing, right? 100 people, easy, right? After a few years of development, maintenance, update, you have this big algorithm with fitting code and all everything, and the total audio processing code. Now you print it out and you see 40 letter or A4 pages of C++ code, right? And yeah, you have 100 people. So let's say you have contributions from about 50 engineers, and some of these engineers have left the company. So you have a serious problem, right? I mean, who really knows your algorithm at this point? You have 50 contributions from 50 people, and some of them have already left. How do you guarantee quality, and how do you go forward, right? How will you improve if you don't know your current algorithm, right? This is not unlike our current situation, and not just our situation. It's for everywhere in the hearing aid industry and outside the hearing industry as well, right? So here you have 40 pages of code, and we're in the business now of trying to improve and maintain these 40 pages of code, and we do that by, let's say 100 engineers, right? Let's say now that the system that I talked about, that it would actually work, right? So what would a design cycle look like? Well, your company has now 5 engineers that just write code for generative probabilistic model of acoustic data streams. So what is that? That means your engineer should say, there's Bert sounds, and they're going to be generated by a hierarchical autoregressive model. That's 5 lines of code. And there are also speech sounds, and they are also generated by an autoregressive model, and that's another 5 lines. So this entire generative probabilistic model is going to take 1 page of code if you print it out, and it's very high level, and it's very specific to the hearing aid industry, right? And you should patent it because it's your idea, it's the company's idea that, hey, speech is well modeled by a hierarchical autoregressive model. These models are explainable and require our domain knowledge. Then all engineering tasks, and think of it, all reasoning with that model, audio analysis, scene recognition, hearing aid algorithm design, source separation, learning of parameters, everything is just an inference task on that model, and everything is just variation of free energy minimization on that model. And everything will just be automatically executed by the toolbox, RxInfer. RxInfer will automatically execute these inference tasks in real time with ultra low power. So you still have 40 pages of code here, but everything in orange is now automated by a toolbox that basically does optimal information processing with the information that it has. And what's the information that it has? Your predictions based on your models, your autoregressive models, and incoming signals. And these other orange code, which is just toolbox, will create the best fusion of that, right? Will then, let's say, decompose these incoming signals into the original sources. So over time, as you go to the next generation, you only need to work on the blue code. That's what's hearing aid code. Everything that's in orange has nothing to do with hearing aids. It's just automated reasoning. It's just optimal information processing, just like brains do. And if I am a drone company, I would use exactly the same toolbox, and I would write here in green my 1 page of code that is my model for how I think the sensor signals are generated for this drone. Or I can build a robot with in 1 page of code, and the other 39 pages of code is just RxInfer. And that's the big thing. You don't need 100 engineers to keep your code up to date. You need 1 engineer because you have split now knowledge from reasoning. Reasoning is automated by a toolbox, and good reasoning is the same whether you are working on a robot or on a drone or on a hearing aid. It's just It's just Bayesian inference, and it's just variational frequency minimization. That's why we can do everything with the same brain, because good reasoning for solving a problem is the same whether it applies to vision or hearing or locomotion or whatever. There is nothing special about hearing other than there is the cortex, the auditory cortex has developed a specific model for how it hypothesizes that sounds are produced in the world, but the inference is all the same. So that means that you get a much more maintainable design cycle. All this orange stuff can take place in the field under situated conditions. You can basically think of this one page as the DNA that describes what's going to be. It's going to be a hearing aid, a robot, or a drone. And so that would be a big pivoting point for a company. Is it going to work, right? I don't know, of course. I mean, this is about the status of ArcSinfer, right? I mean, we do high risk, high gain. This is a high risk, high gain project, right? I mean, we're about halfway in what ArcSinfer can do. It can do a lot of things, and then there are some things, multi-core processing, which I like to do. That is not working yet, right? So about halfway, but it's still, I think it's better than anything that's out there that tries to simulate what brains do. When is it going to work, or is it going to work at all? I don't know. As I said, Carl Friston is, like I said, sort of the leader in this community. He's an extremely impressive guy. I think you should look him up. We also are in contact with Carl Friston. This is what he wrote, what is it, 2 months ago to me. And so he says, your progress is stunning, your vision is in the right direction. So he believes in what we do. That's probably the best thing we can say for ourselves at this point, that he thinks we're doing the right work. And so that's where we are. It's promising, but it's not ready for going in a hearing aid. It is completely different from how hearing aids currently work, but if it's going to work, it would make hearing aid design much simpler, and it would make it very easy for GN to become a robot company and to become a drone company. So I think it's worth it to continue. And so I'm ready for your questions. Yeah.
Hi, this is Philippe.
Okay.
Maybe one question. Nice to meet you, Bert. Great presentation. Really loved it. Super interesting.
Thank you.
My question would be, you say there's one level or one page of high level code written. I would assume that does not include the parameters of the model, right? So all of that is in your mind another model, or how do you perceive that?
Okay. So you would write down a model, like an autoregressive model. You know what an autoregressive model is? It says,
okay. So so that I didn't catch. Yes.
Yes. And an autoregressive model says my output y of t is some parameter w1 times y of t minus 1 plus w2 times y of t minus 2. So it's a function of a weighted function of previous outputs. And that makes sense for speech, right? And these parameters, they may change because speech is highly non-stationary, right? Non-stationary. So then I'll say, okay, then these parameters, I'm also going to predict them with an autoregressive model. And this is why I say it's a hierarchical autoregressive model. So now it becomes a time-varying autoregressive models where the parameters are also predicted, and the parameters of that model are also predicted. But at some point, you have to stop your hierarchy, and there will be some parameters that need to be fit. And those parameters, the interesting thing about this approach is that there is a completely different way of looking at how the brain learns its parameters. It just try to predict future sensory data. So it makes a prediction, and then it senses what is the actual data, and there is going to be a prediction error. And that prediction error then sort of sends a message back into your brain. And if it persists, that prediction error, then eventually parameters will get updated by Hebbian rule or something like that to make predictions in the future more accurate. Because more accurate predictions means less prediction error, which means lower free energy, which is the whole goal of the operation anyway. So better parameters are consistent with lower free energy, therefore free energy minimization automatically updates parameters. In our networks, we can update states, which means variables that change in the order of timescales of milliseconds, like speech. And we can also update parameters in the same way. Parameter updating is nothing special. It's just a slower updating. You can also update structure. That's even slower. We also do that, right? I mean, our brains slowly change, and then in a sense, natural selection is free energy minimization over a long time scale. So we also, the way nature implements structure updating is through natural selection, but this is also just Bayesian inference. So state updating works, parameter updating works fine. Structure updating is something that doesn't work in our toolbox. I mean, it would make everything completely automated, right? Then we would have natural selection in our toolbox, and we don't have that at the moment. But so there will not be such a thing as you design an algorithm and then you have a fitting procedure. Fitting is just variation of free energy minimization over a period of weeks or days, and that's it. There's nothing special about fitting in that sense. Think of fitting just as learning, and think of signal processing as perception. They're the same thing. One is over seconds, and learning is over days to weeks. But it's the same process. It's both free energy minimization, just different timescales. So that's also how it works in our toolbox. It's the same thing over different timescales.
Thanks for explaining. Okay, much clearer now.
Sure.
Check.
Okay, great. And thanks for the question.
Yeah, when there are no more questions, then I'm just going to thank you again, Bert. Thanks.
Okay, sure.
And yeah, if there is any question popping up with anyone, I think they can find you.
Anybody can always call me at any point, even in the middle of the night. I'm, as you can see, more than happy to always discuss this in more depth than you can stand.
Great, thanks, Bert.
So
and thanks to the audience.
Okay, good.
Bye-bye.
Bye-bye.
Take care, Bert.
Yeah, thanks a lot.